Good afternoon, everyone present here. I know after lunch it's a tough time to sit through, and especially on an online session, but I'll try to make it as interesting as possible, though that would just depend upon how well your lunch was. So, in this particular topic, today I'm going to basically discuss how quantum sensing is facing the different challenges and how can we look at this technology in terms of future prospects. Of course, quantum sensing is one of the most fascinating frontiers in modern science, essentially because it combines the basic principles of quantum mechanics, that is, superposition, entanglement, and of course, coherence, and to achieve precision, which is much far beyond what classical sensors can actually do at the moment. Here, I'm going to discuss the core technologies. I mean, of course, all of you are already aware of all these technologies from the past sessions. I'll just walk you through briefly to all the technologies, just kind of a summary rush up, and then some challenges which entails this. I begin with this very famous quote of John Wheeler, who said that if you're not completely confused by quantum mechanics, you perhaps don't understand it. So yeah, of course, I know it's tough call, but this is a very this perfectly basically combines all the principles of quantum mechanics in one particular slide. That okay, if you're not understanding, it's fine. That's how you're supposed to be, right? So I begin with this talk on one basic slide on quantum information science. What is quantum information science? Essentially, is it is interdisciplinary field which combines the principles of quantum mechanics and entails the four basic pillars for which you need the information to be processed, read, and then finally analyzed. So these four basic pillars that we often talk about are quantum sensing, quantum networking, quantum simulation, as well as quantum computing. Beginning from quantum sensing, I can say that quantum sensing is basically the technology where you harness the quantum state's sensitivity to external fields in such a way that it creates sensors which are far more precise than any of the classical versions. Whether we talk about atomic clocks, or whether we talk about chemical sensing, or whether we talk about medical imaging, any of those are the sensors which are currently which quantum sensing hopes to focus is much has a sensitivity, has a precision, has accuracy much beyond classical limits. The second field that we talk about here is quantum networking. Of course, quantum networking, probably you have a different session for that. In quantum networking, we are basically focusing on how the properties of qubits can be used for secure communication without being eavesdropped, or even if it's eavesdropped, we can easily detect this eavesdropping. And here we are basically using the principles of quantum key distributions. The third topic that comes under this pillar of quantum information science is quantum simulation. So what is quantum simulation actually doing? It's basically simulating very complex computation processes. This could be anyway found in nature, maybe physics, laws of physics, or maybe laws of chemistry, or even for that matter, even biomolecules. And must have heard so much about protein synthesis, genome deciphering, etc., etc. All this comes under the field of quantum simulation. The fourth field, which is another very interesting and important field, is quantum computing. Quantum computing basically encapsulates the concepts of quantum mechanics such that it can be used to enable different types of computations, such as for discovery of new materials, where using energy systems, using optimization techniques for quantum finance, or maybe simulations beyond classical computation methods. In this particular field, this particular session is dedicated to basically the whole QT of yours is dedicated to quantum sensing. In whatever words we can say, quantum sensing is essentially a field, a technology, a spectacular method in which we are using quantum systems, quantum properties, or quantum phenomena to perform ultra-sensitive measurements. These measurements includes physical quantities such as magnetic fields, electric fields, acceleration, temperature, etc., with extraordinary sensitivity and precision. What brings this sensitivity and how you are achieving precision is the whole crux of this particular technology. Uh, Essentially, quantum sensing has been, been split between two technologies. One is called the photonic quantum sensing, another is a non-photonic quantum sensing. So as the name implies, photonic quantum sensing is basically related to photonic sensors. And non-photonic quantum sensors encapsulates all other sensors, whether it is atomic clocks, NV centers, ion traps, or any other technology. Depending upon how or which property of atom you're using, we would be able to determine, or we would be able to sense a particular parameter of nature. So of course, what actually do you need in a quantum sensor is a ground state, and then you need an excited state. And this energy difference is how you are basically, and when it basically de-excites, this energy difference is basically where you are encoding your quantum sensing knowledge. Um, Now, if you talk about the basic quantum resources, what we talk about here is the basic principles, the principles of quantum entanglement, those of superposition, and quantum coherence, as well as interference. Quantum entanglement, of course, all of you here, you know what quantum entanglement is, but how it is important in quantum sensing is what I'm going to talk about here. Entanglement is basically a strong correlation between particles. That means the state of one particle is instantly related to the other, no matter how far apart, especially spatially how they are located in the space. In sensing, basically, entanglement is the key which helps us in noise reduction as well as collective precision enhancement. For the sake of example, I can say, supposedly, if you have an entangled atoms in an atomic clock, or maybe entangled photons in any interferometer, now these can perform they can basically outperform the short noise limit of quantum of any classical system. So this here is where quantum entanglement plays an important role when we talk it in terms of quantum sensing. The second important phenomenon, that is that of quantum superposition, is basically, of course, we know that what it is. It is the ability of any quantum system to exist in multiple states at the same time. And this basically is used by quantum sensors to essentially exploit these many configurations simultaneously. And thus it helps in providing, or basically encoding, a huge amount of information extracted from a single measurement. And this is what makes quantum superposition a very important quantum mechanical phenomena for exploiting quantum sensors. So supposedly, if you have a superposed system, it interacts with an external field such as that of an electromagnetic field. The resulting phase difference that you see between its states is highly sensitive to the field strength, and this is where lies the basic importance there. The third important phenomena, that is that of quantum coherence and interference. This is very important when we talk of any kind of relationship between the source and that of the one that has to be detected. Supposedly, for example, we are talking about a phase relationship between these states. So what is coherence going to do? The coherence is basically going to ensure that the system retains a memory of the system, of its quantum phase long enough to accumulate measurable effects. At the same time, interference between these different quantum paths, as we know, is going to amplify these subtle signals, and hence will help us unleash the properties of quantum mechanics and get to us this extraordinary sensitivity that we always talk about in terms of quantum sensing. So we can say, summarizely, we can say that entanglement boosts precision through correlationship. Superposition helps in increasing the amount of measurables information. Coherence helps in preserving it. And all these three things together helps us in making quantum sensing possible. The next thing that I would like to talk about is the requirements of quantum sensor. So we know there are certain De Vincenzo's criteria. Corresponding to these criteria, we have certain requirements of quantum sensor as well. So the first, requirement is that we should have well-defined quantum states. That means any system that is capable of representing a quantum sensor should have discrete addressable energy levels, often represented by Ket0 or Ket1, where Ket0 is generally referred to as the ground state energy and Ket1 is that of excited energy. And these should be separated by some kind of a transition energy. For example, E is equal to h cross omega 0. I'm sorry, there's a small typo there. The second is that we should be able to initialize this and then read out. So which means that the system that is prepared should be reliable so that it can be initialized, the quantum state can be initialized and then eventually measured. For example, I can say that for the case of NV diamond centers, right? In this case, we can achieve it through optical pumping to polarize spins, and fluorescence detection can be used for the final state determination or final state measurement. In atomic systems, laser cooling, optical pumping, all these can be used for initialization of the atoms, while fluorescence or absorption of spectroscopy is basically providing you the measurement thing. The third point that is important is that of coherent manipulation as well as control. So, what is basically required is whatever system you have, you should be able to manipulate it. Unless you manipulate it, it's of course it's of no significance. So, you should be able to manipulate these systems in such a way that you get the desired results, maybe in terms of phase, in terms of change in spin, or whatever it is. So you should be able to essentially easily manipulate this. The fourth thing that we talks about is that it should be able to interact with a relevant physical quantity, right? Such as an electrical magnetic field. Now, this interaction becomes very important because it is basically giving you how one form of energy can be easily transduced to another form of energy. Basically, some kind of encoding is required there, so that the any change in quantity there can be easily studied and then decoded in form of which can be easily understood as from a sensor point of view. Broadly here, I bring towards you the application areas of these quantum sensors. We can see that there are atomic clocks, there are magnetometers, there are gravimeters, the inertial sensors, electrometers, photodetectors. Probably all of you are aware of all these. And in terms of real world applications, there are so many. We talk about precision timekeeping and navigation beyond even what GPS is providing to you. You don't even need a GPS in such in atomic clocks or in such kind of systems. When we talk of biomedical imaging and diagnostics, we are talking about being able to detect one magnetic field even beyond, of course, the classical limit, and thus can be used for imaging techniques such as that of MRI, or can even help in non-invasive brain mapping or even cellular scale magnetoresonance MRI imaging. Then we talk about, of course, physical environmental monitoring becomes a very important part, and these quantum gravimeters are capable of detecting very minute variations in Earth's gravitation, which becomes very important when we're determining the health map of Earth, especially the geophysical as well as other aspects of the Earth. When we talk about material characterization and condensed matter physics, these are another very important areas when we talk about nanoscale magnetic textures and superconducting vortices and stuff like that. Um, uh, for the sake of example, I can say again think of NV centers which can measure local magnetic noise in superconductors, which can reveal quantum fluctuations at cryogenic temperatures. When we talk about quantum sensing, is another very important field is that of energy and infrastructure. In this particular field, we can basically contribute in how energy is resilient to energy system can be made resilient, how you can maximize utilization of electricity, how you can use nuclear energy applications. So all these fields are equally important. We will see how probably you must have already seen how quantum sensors, different types of quantum sensors are relevant to different fields. Besides all these, they are also used to probe. Quantum sensors are currently used in fundamental physics tests, such as exploring the outer Earth. When we talk about dark matter probing, we talk about gravitational waves. We talk about testing the fundamental limits of the classical sensors. So, for example, I can say that if you talk about optical lattice clocks, now these are highly precise and can detect very tiny relativistic time dilatation. Then these can be used for determining the change in altitudes of maybe just a few centimeters, and Maybe if we are more precise, we can go to as low as few millimeters. So we can say, on the whole, the applications of quantum sensing are very broad and interdisciplinary. You cannot see that, okay, quantum sensing is only good enough for timekeeping, or maybe it is only good enough for maybe geological survey. It's good for almost every technology, and this is what makes quantum sensing a very fascinating technology, as I would say. So a very basic difference between classical as well as quantum sensing. So of course, the first thing is classical sensors uses macroscopic material properties. When I talk about macroscopic properties, I basically talk about a huge ensemble of particles. We are like in the case of maybe simple silicon transistor. So the particles that we are considering are those of electrons, right? But here we are talking about the whole jumble of electrons. How those electrons are moving from between two transistors or from input to output. So we are not talking about an electron in one particular electron here. But if we compare this with quantum sensing or maybe a quantum technology, here we are talking about individual quantum particles. Whether we are talking about manipulation or whether we are talking about change in any property of a particle, here we're talking about independent particles. We're talking about how the spin of a photon has been changed, how the electric field has transitioned from one energy level to another energy level. So this is a huge difference in scale at which classical sensing and quantum sensing works. The second important thing, since classical sensing is currently related to the classical phenomena, it is limited by something what is known as standard quantum limit, and of course that's how it is related to short noise, and it arises from statistical fluctuations due to random processes. A in quantum sensing, as we're talking about individual particles, what limits is the Heisenberg limit of sensitivity, and we can say, in a when a classical sensing is limited by one by root n times, while in a quantum sensing it scales down to 1 by n, and this factor of additional root n is one that gives you the multiple nature, the beauty of quantum sensing. The third important phenomena that distinguish between classical and quantum sensing is that of the classical signals can basically classical sensors can basically struggle when we talk about detection of very weak signals, essentially because of interference of noise, or maybe they don't have so very high sensitivity because of relative fraction, which is limited in optics, or maybe the Johnson-Nyquist noise in electronics. In quantum sensing, on the other hand, because we are using the principles of quantum mechanics, such as those of entanglement or coherence, these sensors are very robust when it talk about in presence of noise. And this is what makes them superior in terms of classical sensors, and thus more robust, or maybe they have a higher fidelity, and they have a higher susceptibility to interference noise. So in all, we can say what quantum sensing sensors are doing is basically capitalizing on its inherent property of high sensitivity towards environmental noise. Um, this is exactly what I actually spoke about. It's just a tabular representation. Next is how just a simple flow diagram of how a quantum sensing process takes place. The first step is, of course, the initialization of the step. So the first step is where we begin with the preparation of quantum state, which is known as an initial state, which is, of course, a pure state in almost all cases. Example, again, I can take about NV center sensor. Optical pumping, it aligns the spin into a ground state, while in atomic sensors, or laser cooling and trapping creates a coherent atomic ensemble. The purpose of initialization is, as we all know, is to start from a clean, reproducible state, which can later evolve or maybe transform into a different state depending upon its interaction with the environment, or from this from the phenomena which basically you want to measure. The second step, as we know, is of course where quantum evolution takes place, and it is here we call it the transform. In this system, At this particular step, the system is, or the quantum state is allowed to evolve under the influence of the target field. Now, this target field can be an electric field, can be a radio frequency signal, can be a magnetic field, can be temperature, can be a chemical signal, or whatever. So, but here your initial state is getting evolved in the presence of something that we know as, that they call as a target field. Now, during this interaction, the external parameter, whatever it is that you're measuring, he modifies the system's quantum state as per a certain as per the Hamiltonian, and you get an equivalent Hamiltonian depending on the system. Now, this gets evolved, and your phase is now is encoded such that it is proportional to both the field strength and the interaction time that you're taking. So we can say like system's internal quantum state is now encoded into the information of the target field that you're measuring. The third step that we talk about is, how you are basically measuring this thing. Once the evolution is done, you're basically extracting this encoded information through some kind of readout operation. And now, for example, again, if you talk about NV centers, now this is done through fluorescence detection. So you need to have a very good detector which can detect very high fluorescence with a very high sensitivity. So here the key is that your measurement should collapse your quantum state into a classical state. Now it's from probabilistic to some kind of a deterministic kind of signal. Now this becomes again another important point. Finally, we come to a point where your signal is being processed and you're estimating, and thus this estimation is done in terms of number of shots. And what basically pushes the sensitivity is, now you are pushing your sensitivity close to the quantum Kramer Rao bound, right? These four steps are basically repeated n number of times until you get some kind of probabilistic distribution, and this distribution is basically helping you determine. Why do you need a repeated step? Because quantum sensors, as we know, or quantum technology, is basically highly probabilistic, and based on your probabilities, you would determine what your sensor output is supposed to be. So, in short, we can say that quantum sensing lies in how delicate microscopic process is. The accumulation of this quantum knowledge, this can be converted into a robust macroscopic signal, then which can be easily detected, and finally it can be analyzed and processed in such a way that you get an eventual output to the corresponding information that you're trying to share. So, quantum sensor technology, as I just discussed, there are so many applications to it, and welcome to this quantum system. Now I come to the main part of my talk, which is basically deals with how and what are the challenges in this particular quantum sensing technology. The first, of course, is of course, when we talk about these challenges, we are talking about the real world deployment of this technology. We know that labs all across the globe, even industries working in development of different sensors, but to a large extent, there is a slight delay in the proliferation of this technology in towards industry. Now, why that lag is what explains this particular slide. The first is that it is highly sensitive to environment, and thus the reason behind is the noise. So quantum sensors, as we know, is highly sensitive to environmental noise. When we talk about environmental noise, I'm talking about structural parameters such as temperature fluctuations, magnetic fields, vibrations, RF field, microwave energies, and this is a reason why it is difficult to isolate a quantum system and thereby maintaining coherence. For detection of any signal, it is important, as we all know, that a signal should be highly very different from your background noise. Basically, your sensor should be able to differentiate between your signal and between your noise. Of course, I'm going to discuss this in a bit more detail, of course, here. But what is important here is that any sensor, any detector should be capable of kind of differentiate between the signal as well as between the noise. So your noise should be since we're talking about very weak signals, so and it is perhaps very vulnerable, quantum mechanics is very vulnerable to external noise. Your signal should be such that you can easily distinguish between your background noise as well as the signal. So this is a very important challenge while we talk about quantum sensing technology. Sorry. So second important phenomena is quantum decoherence. That means, which is essentially because when it interacts with the environment, the sensor is like on the verge of losing its quantum state, and it collapses into a classical state. So the second important step is that the second important point is that of miniaturization and integration. As I mentioned, that the labs or whatever research is being done is usually done at lab level, and you see very big, almost a room full of electronics, a room full of optics is there. And when we talk about any technology, we are talking about a palm top technology, which means you should have a sensor which is miniaturized so much so that it can be, it can be easily used. So when we talk about miniaturization, what basically limits is the scalability with which we can win it. Currently, you are all aware that we need most of these technologies need cryostat or very high precise lasers or stuff like that. And getting these technologies, cons- con- uh, confining them to a very small step is one limiting factor of quantum sensing technology. Of course, these are very expensive, cost is very high, and of course, this is one major reason why it is not this technology has not reached the hands of a common man. Then we talk about calibration and standardization. Since unlike the silicon technology, uh, quantum technology is like spread across all the length and breadth of in terms of technology. We are talking about nitrogen vacancy centers, we're talking about superconducting qubits, we are talking about ion traps, we are talking about photonic qubits, different technologies using different qubits. There's no one standard which can be adopted, which are currently at this point if you can say, okay, this is the standard. This this limitation of the calibration and proper benchmarking tools is again a big um, impediment to the growth of this technology. Third is the technical and theoretical development. We all know, aware that we are currently in that near-term intermediate scale. We are still far away from fault-tolerant systems. So, of course, quantum error correction and noise mitigation methods are still in a very infancy stage, and people are working on it, and we still have not reached that state where we can say, okay, yeah, this is what we're talking about, right? Okay, two important phenomena that basically explains the limitation of quantum technology is the noise and, of course, the sensitivity of our system. So, what is noise? At quantum, with respect to quantum noise, I can basically classify quantum noise that disturbs sensors is quantum projection noise, the decoherence, the initialization and control errors, as well as the classical readout errors. Okay, first is a quantum projection noise, and this is a very basic and fundamental unavoidable source of noise for any quantum measurements. So basically, it originates directly from the probabilistic nature of quantum mechanics. So when you're measuring a qubit or any kind of state which is in a superposition, of course, for example, we can say that alpha ket 0 plus beta ket 1, the outcome is random, it is not deterministic. So once you measure it, it can collapse either as in a ket 0 state or in a ket 1 state, with the probability which we know is ket alpha square plus ket or and ket beta square. Even if we prepare the same system identically several times, the results are going to fluctuate. This is exactly the reason what causes quantum projection noise. So, for this particular reason, we have n identical particles. The uncertainty still scales as 1 by root n, which defines the standard quantum limit. I think I have not mentioned here, but SQL, as I mentioned, is 1 by square root of n, which means that if you double the number of particles what improves is just by a factor of root 2. However, if you're using entanglement or spin squeeze state, for example, here you can surpass this limit and you can approach the Heisenberg limit, which is stated here as 1 by n. So this is a principle which is behind the quantum enhanced metrology, and reducing projection noises, of course, through collective quantum correlations. The second cause of noise is that of decoherence. We say that it occurs when any quantum system interacts with the environment, thus leading to the randomization of any feature, such as the phase relationship between the quantum states, right? So here I can take as example of say a block vector is there, right? Block vector of a qubit. So in ideal case, this block vector should precess or maybe rotate coherently, which encodes the phase difference between the internal and, of course, the caused external signal. But supposedly, if your system is now exposed to an external magnetic field or some kind of a temperature drift or maybe some kind of microwave signal or some any kind of noise, what happens is this block vector is going to rotate in such a way that it will not exactly follow how it should be. It can basically dephases out. So this is essentially what it is doing. It is erasing the quantum information. It is damaging the quantum information which we are trying to measure. So this is the effect of decoherence. Here we are basically talking about two time scales, a T1 scale and T2 scale, where T1 is a relaxation time. However, I'm sorry, I did not mention it here, but they are basically characterized by two time scales called the T1 is a relaxation time, which basically tells us how long the population difference between the states is preserved, and second is the dephasing time, which actually is responsible here for the signal contrast, and it is basically how long phase coherence can last between two states, between a cat 0 and a cat 1 state. So, in order to improve the sensitivity, we need to have long coherence times. Since the cumulative signal is proportional to this to time in which your signal, in which your quantum state is exposed to the external signal. Now, how can overcome this coherence? So there are techniques such as dynamical decoupling, there's spin-echo sequences, then there's something called a CPMG, there are quantum error correction techniques. All these techniques are actually focused on canceling the environmental fluctuations. So we say that ultimately what is required is that coherence times is very central to improving improving the performance of any quantum sensor. The third point that comes into picture is due to initialization and control errors. So what we should begin with is, as I mentioned in that Da Vinci's criteria, is that you should begin with a very, very pure and clean state. But is it possible at all times? No, of course. There is a certain kind of imperfection related to that, and this is one of the major reason which causes some kind of errors. And these errors are called the initialization errors, which means when the qubit is not perfectly prepared in a pure state, it's some kind of a mixed state. Now, this reduces the contrast, and which is where your signal contrast is essentially affected. The second important part is that your control errors, basically your pulses which are acting as an external pulses, again is not very clean and clear. So again, this is also a reason by which we get a reduced contrast, and you don't get a very perfect output of when you measure it. There's some kind of bias or drift associated with it. So how do you mitigate these effects? So in order to mitigate these effects, we are basically using compact composite pulse sequences. We are using calibration protocols, some kind of feedback control systems. But of course, all of them cannot be eliminated in entirety. The fourth important uh, cause of noise is the classical readout noise. This is, as the name implies, is a classical time kind of noise, and is associated with how your detector is, and imperfections, basically imperfection associated with your measure with your detector. Again, example, if you take of NV center magnetometry, the fluorescence signal is collected to some kind of optical detector. Now, if a detector has certain kind of, drift or some kind of imperfection, whatever, however your quantum signal is perfect, the output cannot be perfect. So, in entirety, we can say, yeah, there is certain kind of noise, and whether it's photon short noise, whether it's electronic noise, or whether it's some kind of laser magnetic drift. Now, these are the ones which are essentially improving, reducing your contrast and increasing the overall noise. And this can be basically mitigated using improved photon collection, or maybe some kind of very good electronics, using a very highly stable laser, or some kind of signal averaging technique. So if I have to summarize all these four noise, I can say that projection noise is one which sends a quantum statistical limit. Decoherence is basically helping you how long you can, get your external signal interact with your quantum state. And therefore, the longer the time it interacts, the better your signal output is expected. The third is the control on initialization errors itself. It basically reduces the accuracy and is related to preparation and operation kind of time. The fourth is, of course, straightforward a classical noise, and it stems directly from your measurement apparatus. So, what separates a theoretical quantum advantage from the real world quantum device is a menu, or is basically juggling with all these types of noise. And of course, as I said, that different groups working on different technology to get make it better with every passing day. The second important concept, while we talk about limitations of this, is sensitivity. Here's a similar definition of sensitivity. It defines how well a quantum sensor can detect weak signals in the presence of noise. So there's three key quantities that we can discuss about here: is the signal to noise ratio, the minimal detectable signal, as well as sensitivity. So here's a small broad overview about this. So the first is, as we know, a signal to noise ratio, or SNR. It simply tells us how clearly a signal stands out above any background noise, right? So mathematically, it is actually a ratio of the signal induced change in the measurement probability to the uncertainty in that probability, right? So better SNR implies better distinguishable signal. So in quantum sensing, this depends upon the three factors. The coupling strength. The first is the coupling strength between actually your signal amplitude. The third is the sensing time, as I mentioned here, right? Now, longer the measurement times, of course, you're going to have a better SNR. But of course, it is going to be limited. Your interaction time is going to basically be limited by the decoherence time here, or technical noise begins to dominate. Then now from the second important factor that takes into care and that defines it as a minimal detectable signal. This basically defines the smallest measurable signal that yields SNR of 1. So it's a threshold between below which sensor cannot reliably distinguish signal from noise. So there's certain detectable signal which you can measure, and below which it cannot be measured. Now, the smaller this value of Vmin that we say, the better your performance, census performance is. So it depends inversely, of course, on three parameters, as I mentioned: the coupling strength, the coupling constant, the readout contrast, as well as the measurement duration. So from this, we can define sensitivity as essentially how small a signal can be detected. Better sensitivity can be achieved by increasing the contrast, by increasing the interaction time, by having a better coupling, of course. The fourth important factor that explains is the signal integration. When we talk about signal integration, we are basically talking about repeated or continuous measurement, which will allow us average out the random noise. That means if you can improve the effective sensitivity, and this improvement is essentially ensured by by root n times, right? So however, this is only going to work if your noise is uncorrelated to the signal that you are measuring. Once it starts to drift or gets some kind of correlation between the noise as well as between your signal, your averaging will fall flat. So all these are the basic three factors which are going to determine our sensitivity. And what we can say here is that you need short-term averaging improves precision. We can say a long-term averaging saturates once your noise gets correlated. And third is you need stable experimental conditions for long-term sensitivity gains, right? Here we can just summarize the key parameters that are affecting your sensitivity. There's a coherence time. You need the time to be as long as possible. You need the noise to be as low as possible. For sensors which are based on optical stability, which need lasers. Your lasers should be very highly precise, with very small FWHM. Then we talk about materials when we talk about sensors such as those of NV centers or maybe other technology. You need very highly pure materials for to able to develop such kind of sensors. Then your environmental noise should be as low as possible, especially when we talk about maintaining a stable temperature or pressures, which essentially affects atomic densities, coherence, or even laser performance. So all these factors are basically ones that we have to keep in check while developing this technology. Now broadly I think I'm at the end of my topic. So um, essentially here there are five kind of sensors, and and broadly what limits these this technology is, as I mentioned in the beginning. These are the five limitations, and different sensors or different technology is affected differently is works differently because of the inherent nature in which these are done. Probably you all are quite well aware of all these different technologies, and I can say briefly that the factors that limits these sensors are decoherence, their setups, their complexity, their cost, their vulnerability to or susceptibility to external noise, and that's it. And we talk about, if we briefly, if I can I have another 5 minutes, or should I stop here? Okay, okay, I still have, my watch is not working. I'm sorry. Okay. Um, Okay, I'll talk about the future perspectives of this technology quickly. Or basically, how do we look at this technology from the perspective of future? Basically, the landscape of quantum sensing is very looks very bright at the moment, and this field is expected to grow exponentially. Especially, it's a field where there are a lot of innovations happening. Since there's a lot of interdisciplinary work happening in this particular field. When we talk about any of technology, what makes important is how is the market growing, how it is can be adopted across different platforms. The first and foremost is like quantum sensing is basically entering into very rapid growth with applications focused in every field, whether it's healthcare, whether it's defense, whether it's telecommunications, navigation, as well as environmental monitoring. And we are finding there's a we're witnessing a huge transition from lab prototypes to commercial grade quantum sensors. And now these sensors, they're not just precise, they're not just accurate, they're not just highly sensitive, but we are moving towards a phase where you are expecting to get miniaturized and user friendly sensors. The second important future perspective is that about the technological advances. So, technological process is being driven by advances in quantum error correction, whether it is AI assisted calibration or whether it is material engineering. All these advances in different fields are very closely related, and especially when we talk about scaling of these technology, fabrication plays a very significant part in miniaturization of these sensors, moving this technology from lab to your household. Miniaturization becomes important, and for miniaturization, the current technology has to scale up to the point where you can have nanometers of all. You can scale, you can fabricate up to nanometer scale. So you see there's a plethora of advancements in that domain also. The third important in terms of future I can see and talk about is application expansion. So quantum sensing is finding its breakthrough in non-invasive medical imaging, especially MRIs. They can also help in detecting biomarkers or even neural activity in terms of unprecedented precision. In terms of in fields such as navigation, quantum inertial sensors can function even when your GPS is not available. In fields such as geoscience and defense, we see that there are devices which can help in underground mapping of mineral detection, submarine navigation, even determining the health of, as I said, the health of Earth. So these highly sensitive sensors become very important when we are talking about these kind of things. The fourth important perspective is how we see these this quantum research in quantum sensors in terms of interdisciplinary, in terms of collaboration between industry and academia. Progress in these fields will, of course, lot of it will harp upon how this cross collaboration is going to happen. Now, we are basically trying to combine the principles of quantum physics, material science, engineering, computer science. Now, all this technology, when they are packaged or when they are collaboration, when all this is happening in collaboration, we can basically try to overcome the limitations which are currently faced by quantum sensing technology. Now, this can be in terms of whether it is we are talking about fabrication, whether we are talking about coming up with new tools, whether we are coming about which technology can be most suited for which kind of invest. By technology, I mean whether it is a photonic sensor that you should be using, whether it's an atomic clock that you should be using. All these technologies would basically coalesce into and move together when we talk about collaborative research. Now, here is a very simple summary how we can see how publications have grown over the past 25 years. So we can see that by the 1994, there were hardly any number of papers. We have seen now there's a huge growth in this particular quantum sensing sector. Now we see that there is a remarkable growth trend, and this essentially is in different fields, whether it's quantum materials, quantum devices, and of course, this is unprecedented growth. This means this graph, if basically effectively reflects how your quantum sensing has been on a continuous rise. Number of publications in quantum science has been on rise, and which indicates itself how research is transitioning from fundamental physics to the real world applications and their prototypes. This means the surge in publications itself makes quantum sensing a very important pillar of quantum information science and an active area of research for all those who are interested in quantum in research in this field. It's a very vibrant field, and not just because it's very fascinating, also because this is one field where interdisciplinary work is going to be acknowledged, whether you're from a biological background, whether you're a physicist, whether you're a chemist, or whether you are from a financial background. This is one technology where you can find your space. So the next, yeah, this is again very interesting graph that I found across on the net. Now, in this particular field, you see how your it's basically forecasting how your quantum sensing technology is going to scale up. So we see that by in 2019 it was just 1 billion of investment here. So, and by 2028 it is found that is going to scale up to almost 2.5 billion. So this is one graph, another which is showing how your future of quantum technologies is is going to affect the rest of the world economy. So if you see, I mean, these are the different kinds of sensors that have been kind of encoded here. If you see the different sensors, I can still say that atomic clock still remains the largest and the most mature technology here, and it continues to dominate due to established application in, of course, navigation, telecommunication, and synchronization. The second important sensor is the quantum magnetic sensors. We're reflected here in yellow. They also show a very fast growth, and they're expected to overtake other categories, and they find huge applications in MRI, in medical imaging, such as in MRI, in defense, as well as in geophysical applications. The third is the segment that we can say is the gray one, which basically relates to gravitational sensors. And this particular is again, these are very niche areas, but it is again very promising. It is can be used for monitoring of Earth, for underground mapping, and for aerospace navigation. Then you have single photon detectors reflected here in green. Now, these and quantum LIDAR sensors, they currently are emerging technologies, and they support quantum communication as well as imaging. And they have a strong synergy between them, and this is why they become very important. Now, there are other sensors, there are some other quantum sensors, and this is a broad area, and this represents again a rapidly evolving technology. And under this comes the hybrid technology, which basically combines the pros of different technologies, whether it is a photonics with superconducting, or maybe NV centers with ion traps. So those all are coming under the classification of quantum photonic sensors. So we can say that one of the major why the reason behind these the growth of these sensors is essentially because there is a huge investment, both in terms of both by the government as well as private equities or private companies. Then there is also what I can think about is, of course, there is in terms of tools and fabrication, there has been a huge improvement there. Um, I mean, discovery of new materials, also known as quantum materials, has basically helped in the growth of this sector. Then there's, of course, there's some kind of a commercial readiness of these technologies. We firstly, which were just considered just in the lab level, they are now they are into that stage. There's certain maturity to this technology, and people are accepting them, and they are believing in this technology, which is why you see this spurt in growth from 1 billion to maybe almost 3 billion by the end of the next decade. uh, yeah, I would conclude my conversation on my presentation with this Nobel Prize in Physics by three phenomenal scientists: John Clark, Michael Devere, and John Martinis. Now, this was, of course, given to these scientists for the foundation of superconducting quantum circuits, which forms the background of many quantum technologies at the moment, right from quantum computers to maybe ultra sensitive quantum sensors. So, John Clark basically pioneered in SQUIDs, that is superconducting quantum interference devices. These are again very important when we talk about detectors, etc. And they help in ultra precise magnetic field sensing. Then there's Michael Devere. He has been at the forefront in the development of Josephson parametric amplifiers, as well as quantum limited microwave electronics, and basically, the readout of the qubits. John Martinis has been a Googler for long, and he is the one who has been behind the claim of quantum supremacy of Google. And he basically demonstrated high coherent superconducting qubits. Um, now, this year's Nobel Prize is, we can say that it directly ties our discussion to quantum sensing technologies, essentially because many of the today's sensors are, whether they are magnetometers or whether they are gravitational detectors, many of them still rely on superconducting quantum effects. And this is why this particular slide, I mean, I wanted to keep this in my presentation. So we can say that their discoveries have played a very significant and have been very instrumental in the development of quantum sensing. Um, Essentially because they have shown or demonstrated how you can measure very weak signals, whether they're magnetic fields, voltages, or in gravitational waves, with quantum level precision. And broadly, we can say that this award signifies how quantum coherence, quantum tunneling, which were once considered as an abstract theoretical idea, is now being can be practically demonstrated. And they basically, quantum processors are the next generation processors, and we are all witnessing how this technology is growing, and perhaps this is the reason behind the conduct why these different quantum QTs are being conducted. And I would like to conclude that this Nobel recognition is both a celebration and a signal, and it basically uh, celebrates how the different physical principles of quantum computing and different quantum metrology and sensing are basically, combining and integrating at one point. So, yeah, thanks and questions.
Thank you, madam. Thank you for nice talk and summarizing almost all the aspect of quantum sensing. And yes, there are queries on the in the chat box.
Okay.
Uh, shall I moderate, or you can also see the
If you
queries?
have any, you can just give me a few questions. I'll like to answer them.
Okay, so from K. Lakshmi Narasimha Rao,
Yeah.
he's asking about, can you please explain how background noise can be reduced by quantum entanglement?
Okay. So you cannot reduce background noise. What you can is you can overcome your background noise using quantum entanglement. This is why entanglement becomes important, because you are basically tying two you're basically tying two qubits at the same time, so that even if one is affected, you can find the effect in the other qubit. So that is how it is able to you are able, you cannot reduce it, but you can, kind of effectively reduce the effect of it, and that becomes important in quantum sensing of very weak signals.
And uh, there is one more question regarding the reference books.
Okay,
Uh,
I forgot to
so,
mention that.
Mr. Jagdish, he want to know some reference textbooks and literature to go through all these concepts.
Okay, what if basically there are many reviews which are very good reviews which are available, published by different labs across. What if I share this with you over your mail? Will that be fine?
Yes, so we can share the study material in the Canvas. So if you can provide some, then we will upload to the course.
I'll definitely do that.
Okay, so mm, there is a
Somebody
question
asked me
from,
if they can get my email or whatever. So if people are interested, they can connect me on my LinkedIn.
yes, that will be great.
Huh, you
So
can just
people can
enter
directly
again.
write to you and further discuss the concepts.
Yeah, yeah, yeah. That's
Yeah.
perfectly fine.
So one more question is, how can quantum sensor be integrated with AI and classical electronics for hybrid systems?
Um, Currently, I don't see. Basically, see, AI cannot. AI is again a classical part, right? So you cannot say that it is you're integrating. AI is some kind of technology where you can just help in, classification of some kind of a signal, right? So whatever information you receive through quantum measurements, you can train on the basis of that, and then you can, kind of use AI for better signal understanding. But if I say AI becomes an alternate to quantum sensing technology, or maybe how how you can use AI. So this is how you can use AI at the moment. What I can think about is right from the top of my head. So you can train your signals, or you can train your model based on the output that you're getting from quantum sensing, and that is how you can integrate AI with quantum sensors, right? For better
Okay,
classification.
thank you, madam. So maybe I can take one more because we are running little late in the session, and I would like to uh, suggest the participant to directly approach the madam by writing email, as
Yeah,
she
yeah.
is
You can
willing
connect me
to
on my
help you
LinkedIn.
out directly.
Yeah.
Okay, so the last question may be, which industries are expected to benefit most from quantum sensing in the next 5 to 10 years?
Of course, I showed you a small snippet of it. Atomic clocks, as I've seen that atomic clocks form is a very important technology, which is of course at the back foreground of quantum sensing technology, essentially because of navigation, and of course this is defense, which I'm talking about. I'm talking about navigation, maybe even the mobile technology, because it does not even need a GPS system. So this is one technology, this is one field. Besides, as I said, medical imaging is very can be used, can be, using quantum sensing, you can have a very highly precise sensors for medical imaging. So again, that is another area, or maybe another industry, which I think can benefit from this. In terms of industry, is like maybe medical science, or again navigation industry, defense. Yeah, these are the technologies where we can see there's a lot of improvement in this technology, where we can see a lot of relevance of quantum sensing.
Yes. So
Yeah. Thank you. Thank you so
thank you
much,
much,
ma'am.
madam. Really
For
sorry that
time.
we
Yes, we
may
are.
not be able to go through all the queries right now.
That's fine.
Maybe if you are available in the valedictory session, we'll take some live discussion with the participants. That will be great.
It could be a bit
Till
difficult for me. I
Yeah.
have a meeting. I canceled my meetings initially, and now I put it all the meetings back there.
Right,
that
right,
will
sure.
be great if you can join, ma'am.
I'll,
Till
Five
I'll
to
sir.
try.
5:30. It is from 5 to 5:30, ma'am, in case if it's possible.
Okay, if it's
Otherwise,
possible,
that's
I'll definitely try
right.
it.
Sure, sure.
Okay.
Thank you. Thank you so much for your
Thanks for
valuable
all the
time. Yeah.
participants, and thanks for the organizers for inviting me to this talk.
Okay.
Thank you.
Thank you so much, madam. Thank you.
Bye.
Manoj, you are on mute.
Good afternoon, madam. Sorry, we are little late. So
Afternoon. That's okay.
So we'll just break the session so that two lectures are separated, and then we'll restart maybe in few seconds.
Okay, okay. Should I just